Thanks everyone for coming to this special edition of For the General User. I'm Nathan Laporte. I'm the director of Giant Fab, and we're happy to welcome a presenter from Lesker. We're gonna just wait a couple more minutes to make sure everyone can get signed on, and at about 11:05, I will go ahead and introduce JR, and he can kick it off.
Okay.
All right. I haven't seen anybody else new sign on in a minute or so. So thank you all for coming to this edition of For the General User. We're really happy to welcome J.R. Gaines from the Lesker company. And he's going to be talking about some vacuum deposition, physical vapor deposition, and film growth models. J.R. is the technical director of education at Lesker, and he coordinates and delivers the Lesker University teaching events, which is a great resource that they're very generous to offer us at no cost. He's going to be talking for about 2 hours. He'll talk for about an hour. We'll take a 5-minute break and then do the second hour of the seminar. So there'll be a break in the middle. Of course, you're on Zoom, so feel free to get up, stretch. We've got all your microphones muted, so you don't necessarily need to worry about making a lot of noise. And yeah, I think enough from me. Take it away, JR.
Great, thank you so much. It's just a real honor to be with you. Again, I'm sorry I can't be there face to face in these challenging times, but maybe this time next year we can see each other in person. Hey, here's my contact information. If you need to get a hold of me, again, my email address is right there. Here's my phone numbers, but don't ever call me. I never answer my phone unless it's my wife. This morning we're going to go through evaporation by thermal and E-beam, and then we'll have a sort of a 5-minute break in the middle of this, about an hour from now, and then we'll talk about magnetron sputtering, and I'll go through some of the different power supply options on sputtering and try to show you what those power supply options will do on the morphologies and kind of the performance of your films. And if we have time at the end, I'll talk a little bit about thin film growth models. That's kind of where the rubber meets the road, and hopefully we'll have a chance to get to that. For those of you who have a chance to go to our website, it's really an awesome tool for vacuum technologists. I'm really proud of what my team has built. If you're interested in building your own vacuum systems, there's a thing called Vacuum CAD that you can sign up for. These are all free services. That'll get you access to something like 15,000 downloadable CAD files that you can put into your CAD systems and use those to build your vacuum systems. As I travel the world giving these lectures, the engineers I talk to and teach with actually tell me the drawings are accurate, the holes line up, so it's not just clever marketing, it's actually a tool you can use. If you want to build a vacuum chamber from scratch, you can reg up for this thing called Chamber Builder. And that'll take you, give you some options on whether you want a spherical chamber or a cylindrical chamber or box chamber. It'll let you add viewports and load locks and feed throughs. And when you're all done, you can get a sort of a downloadable 3D rotatable image of the thing that you designed. And I think it'll give you a budgetary price. It's a pretty clever tool. And then this is my part of the site. And so if you've got questions on vacuum, either thin film deposition processes, or you've got a vacuum system that's not working correctly, or you've got an old piece of equipment and you don't have a manual for it, you can go to this part of our site. It's kind of located down in the base of the home page. You can fill out a form, and that comes to me or one of my colleagues, and we'll usually get you a quick email back saying we've received your request and we're on the case. And usually we get you straightened out within 24 hours or so. We get several thousand questions a year on this part of the site. So I'm really, really proud that we offer this service, and hopefully it will help you make fewer mistakes in your career. Hey, there's lots of books out there in thin film technology. The ones in green are the ones that I use in my lectures. There's really no one thin film book that I would say is the answer completely. I would suggest that you have several of them on your shelf if you can. Mossel's book is pretty massive. If it fell off a shelf and hit you on the foot, you'd be hobbled up for months. Vosson's book is pretty decent. Again, a lot of these, and they've got bits and pieces of things that you really need to know to be a great thin film technologist. And again, if you've got any sway over your librarian, I would suggest that you have a few of these on the shelf. Now, just let me talk for just a second about fundamental vacuum. Just know that, if we're at 1 atmosphere, if it were sea level and room temperature, we've got a whole bunch of molecules around us, 2.4 times 10 to the 19 molecules per cubic centimeter, 24 quintillion molecules, and those things are really our enemies. We've got to really have some robust strategies on how to get rid of those things so that we can make pristine thin films. When we look at the composition of those molecules, generally speaking, from a layman's standpoint, it's sort of 80-20 oxygen, nitrogen, maybe 1% argon, but our pumps do a great job at getting rid of those molecules. And so by the time we're down to low pressures, we're really stuck with these molecules. And so we've got some CO2, we've got a little bit of neon, we've got 5 parts per million helium. We like that because we're going to use helium later as our tracer gas on leak detection. We got a little methane, we got some hydrogen, and then again, water. At almost any pressure you go to, at almost any pressure I can get you to, you're always going to have an enormous amount of water vapor in your vacuum systems. And you really got to be super mindful as a vacuum technologist to try to keep your systems under vacuum so that you can fight off this horrible, horrible thing called water, and we'll talk more about that in a little bit. These molecules are moving at really high speeds, and this is in meters per second down here. So we've got nitrogen moving up around 475 meters per second, helium moving up over 1,000 meters per second, hydrogen on its way to 2,000 meters per second. So these things are really, really flying along there. If we had a chance to talk about vacuum pumps, for example, I'd show you how some of your vacuum pumps are specifically designed to match the speeds of some of these pesky molecules. And there's really no negative pressures in our environment. You know, if we're at atmosphere here, we've got our 24 quintillion molecules per cc. As we go down in pressure, as our vacuum systems literally claw these molecules out of our vacuum systems, we go down and down and down in molecular density. We get down here to ultra high vacuum, the edge of it, maybe we still have something like 325,000 molecules per cubic centimeter. You get out here to 10 to the minus 12 torr, and that's sort of the lowest possible pressure you can achieve on this planet. Using every heroic means I can describe to you, and you still have something like 32,000 molecules per cc. And then even if you get out into deep space, you know, if you get out away from the Earth and away from Mars and planets that are still losing their atmosphere, you still have something like 4 to 5 atoms of hydrogen per cubic meter. So not cc's anymore. Now we're talking about cubic meters. So you still have a few little molecules floating around. Atomic oxygen or atomic hydrogen is pretty aggressive too. So it's a pretty nasty environment out there in deep space. Now, as I mentioned, as we go down in pressure, you know, at atmosphere, we're sort of 80-20 oxygen, nitrogen, a little bit of argon. As we go down in pressures, we get into the ultra high vacuum, for example, those gases are gone. They're out of our system completely. And so we may still have something like 32 million molecules per cc left. So we've still got some CO2, we've got some methane, we've got some carbon monoxide. But now notice that the big gorilla in the room, once we get into ultra high vacuum, is hydrogen. Hydrogen's incredibly tough to pump. It's a really sticky molecule. And so for those of you trying to do nitrides and things like that, I mean, this is really your nightmare, is all this hydrogen. It's 80% of your environment once we get into high vacuum or ultra high vacuum. And then notice still, even at this tiny, tiny pressure, we still have an enormous amount of water vapor to deal with. And we'll talk a little bit more about that later. I just want to take a quick moment just to remind you all about this thing called mean free paths. When I say mean free path, I mean the average distance that one molecule has to go before it collides with another molecule. And so you can imagine up at atmospheric pressure, up at 760 torr, when we have our 24 quintillion molecules per cc, that mean free path is a pretty tiny number. But as we go down in pressure, again, as our vacuum pumps literally claw these molecules out of the system, we get down to what your dry scroll pumps will do, or maybe your rotary vane pumps will do, and that mean free path starts to open up. You know, maybe it's a couple of inches. We get into high vacuum, you know, what your turbo pumps and your cryo pumps can do, and now that mean free path is several thousand centimeters. That's really why we like to start doing our thin film depositions down at these sorts of pressures. You still got a lot of molecules there, but now the mean free path is quite large. We get down into ultra high vacuum, maybe the base pressure that we can achieve on this planet using every heroic measure I can describe. You know, these are the pressures that that your particle accelerators are operating at. You know, and now your mean free path is an enormous number. And at those kind of mean free paths, you've got some right to expect you can take one molecule up to the speed of light and crash it into the path of another molecule without it getting knocked off course. All right. Enough of fundamental vacuum. So when we talk about making films now, again, we're talking about some kind of a technique where we're going to transfer some kind of a solid, typically, into a vapor. And with thermal and e-beam evaporation, we're going to do it with heat. With sputtering, we're going to do it with collisions of ions of some kind of an inert gas like argon, or I'll show you some data on krypton. We're going to take that vapor. We're hoping it's going to go across a throw distance and land on a solid surface. We're hoping that once it gets on the solid surface, that it's going to start to nucleate into some kind of a structure. A film is going to grow there, and then hopefully the film is going to have the properties that we want. And if it doesn't have the properties that we want, hopefully there's going to be some kind of a post-deposition process we can do to get you what you need. There's a blank slide just for notes. Again, we would talk about these thin film deposition processes. You typically start out with a substrate. And again, the substrate is clean, it's pristine, it's never been touched by human hands. I'm sure none of you have ever touched anything going into a vacuum chamber with your bare hands. That's an absolute no-no. You can never touch anything going into a vacuum chamber with an ungloved hand. One fingerprint has got about the same number of molecules in it as a cc of air at atmosphere. All right, so we've got our absolutely clean, pristine substrate. We may want to temperature control the thing. We may want to heat it or cool it, depending on what kind of morphology we're trying to develop. As we talk about thin film growth models later on, I'll show you some examples of what we can do if we heat our substrates. Or when we heat our substrates, we're essentially adding energy to the add atoms that are arriving at our substrate and helping them form a more dense, more smooth film. We've got some kind of a throw distance between the substrate and our source, and the source can be your evaporation pellets, your sputter target. We're going to then develop some kind of a flux from that source. Again, with thermal annealing, we'll do it with heat. With sputtering, we'll do it with collisions of argon ions, for example, and hopefully we'll get a film. And hopefully that film will have the properties that you want. And if it doesn't, hopefully there's some post-deposition process that we can do to get your film to do exactly what you need, like stick to your substrate. Now, I apologize, this slide's pretty busy, but I just wanted to show you everything that goes into this. So as a thin film technologist, you're really interested in these things. You're really interested in some film properties, electrical conductivity, maybe optical reflectivity. You might be interested in hardness, things like that. But for you to get the properties that you want, all of this other stuff has got to go right. And so you've got to have a vacuum system which is designed correctly, where you can get to the pressures that you need to. You know, it may have load locks if you're trying to get into some ultra high vacuum routinely. You might need to have the right kind of pumps. You may have a process, for example, that's sensitive to hydrocarbon pump oil vapors, and so you've got to use dry scroll pumps instead of rotary vanes. Then you've got to have a process that works, right? So you've got to have the right current and voltage combinations. If you're doing thermal evaporation, you've got to be at the right base pressure, and I'll show you how different base pressures will affect the morphology of your film. You've got to be mindful about the chemical purity of your source material. And then you've got some fundamental parameters, things which are going to be really a function of the type of process that you've chosen to deposit your films. You know, based on the process, your add atoms are going to have a certain amount of energy, which may or may not be sufficient for what you're trying to do. You know, I'll show you some data on flux densities in terms of things like deposition rate, the angle at which these fluxes actually impact your substrate's critical, and you have a little bit of influence over things like that. I ranted a little bit about substrates. Again, I don't think people spend near enough time preparing their substrates. Again, they have to be clean, pristine, never been touched by human hands. Even if they're super clean, you still got to be mindful of any surface defects you have on the things, because surface texture, defects in your substrates, inclusions, things like that are going to affect how your films are going to grow. We may want to temperature control the things, either heat them or cool them in order to affect the morphology of your film. And then once we deposited the film, hopefully it's going to have the right grain size. Hopefully it'll have the right grain orientation. I'll show you some data on that in a little bit. And if all of this stuff goes right, if everything, all of this goes perfectly, then you'll get the properties that you want. So again, these are incredibly complicated processes, and I encourage you to be really, really mindful about what you're doing. Now on base pressures, let me just mention to you that, you know, talk about mean free path a little bit. So again, if we talk about getting into high vacuum, 10 to the minus 6 torr, just keep in mind that even at that low pressure, you were depositing a monolayer of water on your thin film substrates every second. I mean, that's how much water is in your vacuum systems. If we go down a decade in pressure, we can extend that time to form that monolayer up to maybe 10 seconds. And keep in mind, a monolayer of water is 10 to the power 15 molecules per square centimeter. So if you're trying to get something to stick on your substrate and it's got 10 layers of water on top of it, you're going to have a tough go of it. So if we go down in a decade, we get another 10 seconds. If we go down another decade, you know, again, we're up to a little, you know, sort of a minute and a half or so before you develop that monolayer of water. So generally speaking, the lower in pressure you can go, and even in sputtering, the lower in base pressure you can go before you actually go up to your operating pressure. The lower in pressure you can go, the better the films are going to be, the less sort of inclusions of other kind of strange gases you're going to have. Let me just show you some examples here. Again, I have one of the great jobs in the world, and that I get to travel the entire planet and give lectures to wonderful groups like yours. I teach a lot at national labs and military labs, and I teach with a lot of industrial customers, and one of the groups that I work with a lot are the groups that are doing your automotive lighting. And so these are the people that do the headlights and taillights for your cars and your buses and your motorcycles. And that group should be pretty much interested in reflectivity. And so here's the reflectivity of some kind of common metals over the optical spectrum, so 350 up to about 750 nanometers. And you can see that silver is really the great reflector. All your great telescope mirrors are coated with silver. It's just a wonderfully reflective material. If you do it right, you can get almost a 100% reflectivity. But your car people are too cheap to use silver, and so they use aluminum. And for those of you that have deposited aluminum films, you know it's a horrible material. It just really doesn't want to be aluminum metal. It wants to be aluminum oxide or aluminum nitride. It's just a real pain. So if you've got any extra oxygen in your system, you are immediately going to crush the reflectivity of your aluminum films. You'll go from 85% reflectivity for a pristine film down close to 70% for a film that's got a lot of oxygen in it. And from a practical aspect, if we look at, let's say, car headlights, and this is a study done by the Insurance Institute of Highway Safety, where they looked at the 2016 model year cars, and they evaluated all the cars for the quality of their headlights. And just to give you a little factoid here, a headlight is considered good if it will give you 5 lumens of light at about 325 feet on your low beams. And to give you a comparison, a full moon on a clear night gets you 3 lumens of light. So this is slightly better than a full moon on a clear night. And then your high beams are supposed to give you 5 lumens of light up around 500 feet. And so notice this is a BMW 3 Series, not an inexpensive car, and its headlights were rated poor by the Insurance Institute because they were, again, 5 lumens of light at about 125 feet on the low beams, and 5 lumens of light under 400 feet on the high beams. And why is that? If you look at what automotive lighting guys do, an automotive lighting manufacturer will make 250,000 pairs of headlights a month. So these guys are really built for speed. They're not built for reflectivity. So if we think back about mean free path, and let's say this is our source of aluminum here, and here's our aluminum substrate up there, you know, at atmospheric pressure, we've got way too many tramp molecules in our system. We have no right to expect that we can generate an aluminum molecule here and that it can travel to our substrate. There'll be too many collisions, too much energy lost. The aluminum metal is going to react with the oxides and nitrides and make anything other than what you want. You'll make no coating at all. As we go down in pressure, though, maybe we get down to maybe 10 to the minus 4 torr or so. We've eliminated a lot of those molecules, and we do now start to open up some pathways here, but we're still going to have lots of collisions. And so the aluminum molecules that get here won't have much energy. Most likely they will have collided with some oxygen or some nitrogen in that path, and they'll have, you'll make aluminum nitride or aluminum oxide. Not a great reflector. It's only once we're in high vacuum that we've got these big open mean-free paths, and we have some right to expect that we can make a pristine thin film. Again, most of your automotive lighting manufacturers are doing their depositions about in here, and that's why a lot of these films are pretty junky. Here's a really simplified cartoon for a thermal evaporation system. Again, this is about the most simple system that you'll work with in your careers. Again, your material sits down here in a boat or a crucible. There's a power supply, again, that I'm not showing you, but the parameters of the power supply are critical. You've got to know the voltage and the amperage of what the power supply can deliver in order to determine what materials you can actually evaporate. Anyway, so your materials are down here. Your substrates are typically up high. Generally speaking, we're going to evaporate up. I'll show you a boat here in a minute where we can evaporate down, but it's fairly complicated. Hopefully your substrate's on some kind of a manipulator so we can actually move it through the vaporplex that we're going to develop here. This chamber, again, can be at the lowest possible pressure that you can achieve. So 10 to the minus 8 torr is not a bad number for a thermal or E-beam evaporation system. You do not need a process gas. And so the lower in pressure you can get this system, the more pristine the films are you're going to make. So you'll have fewer gas inclusions, fewer stacking errors and things like that. So again, think clean, pristine, lowest possible pressure you can achieve. You're typically going to have a quartz crystal microbalance, so you can measure deposition rate in real time, and obviously we're going to want to measure pressure. Because if you want to make two films that are identical, they've got to both be done at the same base pressure. If you don't get to that same pressure, you're going to make really horrible films. Again, and I'm not showing you the vacuum system that goes along with this. A lot of people want to use thermal evaporation, for example, to put gold on things, to put gold contacts on things. And so this is where a little bit of material science comes in. My marketing guys are crying back in Pittsburgh. I couldn't find an image of this, so I drew it myself. So if I want to put gold on glass, for example, you know, glass is essentially a big oxide, and gold doesn't want to stick to oxides. And so if you try to put gold directly on glass, it'll just peel right off. And so you typically use an adhesion layer, something like titanium or chrome. And so if you put titanium, for example, onto an oxide that likes it because it performs titanium oxide, one of the versions of titanium oxide at the interface, and so that sticks pretty nicely. And then we can put our gold on top of titanium. And if we do this all without breaking vacuum, you can get your gold to stick to titanium pretty nicely. Now, if you have to break vacuum and expose your titanium to the atmosphere, you're going to have a titanium oxide layer here, and your gold won't stick to that. So just be really, really mindful when you're trying to put metals on things. Certainly gold, that gold does not want to stick to oxides, and so you've got to be have a nicely sophisticated system to do that. Okay, so again, when I talk about thermal evaporation or evaporation at all, it's about vaporizing the material. Thermal and e-beam evaporation is really not about melting the material. So we're interested in the melting temperature because it's going to have some effect on how the material is going to react with our boats, but we're really not intentionally trying to melt anything if we can get away with it. And evaporation and sublimation are different. So evaporation we're going to do with heat. You know, sublimation we can just do with pressure. So I'll show you some charts in a couple of seconds where we can just sublime something if we want to make a film out of it. These thermal evaporation systems are really, really simple. You know, here's one of our older Nano 36s. I think we have a newer version now, which is a little bit more fun to use and a little more compact in terms of its footprint. But again, you know, in this case, we've just got a very, very simple stainless steel box chamber. Our boats are down here. Our substrates are up here. Really, really simple setup here. We've got a power supply. We've got a monitor here to look at things like quartz crystal microbalance. We've got an emergency stop button here. I'm not sure why we have that, but maybe our attorneys made us do that. Again, very, very simple little systems. If you look down inside the system, again, this is a brand new system. So it's clean, it's pristine, it's never been used before. This is a 3-boat system. So we have a boat here, we've got a boat here, we have another boat here. The boats are typically made out of refractory metals like tantalum, titanium, or molybdenum. There's a little indentation in the center of the boat, and that's where we're going to put our materials to evaporate. This has got a shield in the center of it here to try to isolate one boat from another, but just know that everything goes everywhere. So there's no very clever ideas on how to really keep one boat from contaminating another boat. So just be really mindful about that. This system is set up with a shutter so that I can swing this over the top of the boats and preheat my source material and try to desorb off all of the water that might be on the material, try to burn off any fingerprints that some sort of an incompetent technician put on my material before I tried to do the evaporation. This is, again, widely used in industry. And if you go out into the world, and certainly at some point you will graduate and go out there, if you go to an automotive lighting facility, if you want to go and make headlights for Aston Martin or Harley Davidson or Cadillac. Those are all done by thermal evaporation of aluminum. And so they would put in a whole bunch of those plastic substrates, which are going to be your headlights, and a bunch of aluminum canes in here. They're going to close this door onto this thing. That's the basic evacuation system there. They're going to hit a button here. This system is going to go from atmosphere to 10⁻⁴ torr. They're going to do a deposition and come back up to atmosphere in under 4 minutes. Incredible. That's why your headlights are so horrible. Then they're going to open that door here and then close this door, hit the button, and do it again. And they'll do them as fast as they can, 250,000 pairs a month. You got lots of options on thermal evaporation boats. There's lots of different geometries on these things to try to affect the shape of the flux that's going to come off of them. Again, as I mentioned before, we've got to be really, really mindful of the voltage and amperage of our power supply, because that completely dictates the suite of materials that we can make by thermal evaporation. We're going to be a little bit mindful about compatibility with the thing that you're trying to evaporate in the boat material, and I'll show you some recommendations here in a minute. And then obviously you need to be mindful of the thickness of the film that you're trying to deposit. Again, I showed you these boats. Again, these are great for using for making relatively thin films, because you can't put much material in them. You can evaporate from rods by putting coils in there in our systems. If you do want to evaporate down, for example, if you've got a substrate that needs to be coated on below your source material, there's some fairly sophisticated boats out there that'll evaporate down. If you've got a material that spits a lot, you can put it in what's called a baffle box, where we put the material in the box and then cover it up with a sort of a shield to try to mitigate big clumps of material spitting out at your substrates. If you want to try to make a thicker film, we can graduate to crucibles, or if you don't like to reload your system after every deposition, we can use a crucible. But now we've added a thermal interface. So the crucible itself sits inside a basket. So now we have a thermal interface between the basket and the crucible, and then the crucible and your source material that goes on the inside. And your crucibles can be things like aluminum oxide, silicon dioxide, pyrolytic graphite, metals like tungsten or copper, boron nitride if you don't want your material to stick very much. Hang on a second, my dog wants a cookie here. Hang on. All right, there you go. All right, the dog's happy for another few minutes. Now, if you want to try to make organic thin films, if you want to try to make thin films from materials that say vaporize at relatively low temperatures, like 1000 C, you can use these really nice low temperature evaporation guns here. You can see here that we've got it's got an aluminum oxide crucible, but you can see it's got heater coils all through here. And notice that the distance between the heater wires gets smaller and smaller and smaller as we get up toward the mouth of the gun. That's so we can have a temperature differential across the height of the gun, so that we don't redeposit material here at the mouth. Very clever. So again, there's going to be some things that you can do by thermal evaporation here, low temperature stuff, or the boats that I showed you, the tantalum, the molybdenum, the tungsten boats. For other things like refractory metals, if you've got something that goes off at very, very high temperatures like platinum, tungsten, titanium, things like that, we may be better off doing those by an E-beam. I'll show you some data on that in a second. Now, for all of these things, for thermal and E-beam evaporation, we're very, very much interested in the equilibrium vapor pressure of the material that we're trying to deposit. Now, everything's going to vapor. Anything solid is trying to be a gas. And you remember as a kid, you probably did an experiment where you put a bell jar over a beaker of water, and over time, you got to some sort of an equilibrium point where you got a certain number of molecules that were gaseous and a certain number that were liquid or solid, and that the exchange rate after some period of time became equal. So we had molecules going from gas to solid, and some molecules going from solid to gas, and that exchange rate at some point reached an equilibrium, and that's what we're talking about, equilibrium vapor pressure. And typically for thermal and E-beam, we want that equilibrium vapor pressure. We want the vapor pressure of this gas here to be somewhere between 10 to the minus 4 and 10 to the minus 2 torr. I'll show you some data on that in a second. Now, if we're trying to get to the number there, what temperature do we need to get to that equilibrium vapor pressure that we want, I'll show you some of Rick Honig's wonderful charts that he developed when he was at the Radio Corporation of America. There's some other places that we can look these things up, and we can actually calculate them using equations if we like to do the math. I'm typically too lazy to do stuff like that. If you just want to look it up, again, these are the kind of a color version of Rick Honig's equilibrium vapor pressure charts. very, very handy. Unfortunately, he only did these things for single element metals, and so it doesn't really help you out if you're trying to do oxides or nitrides or sulfides. But if we're just trying to do a single element metal, let's pick one like zinc here. And this tells me here's equilibrium vapor pressure over here in this axis. And so 10 to the minus 4 is here, 10 to the minus 2 is here. Let's say we want to be right in the middle, 10 to the minus 3 torr. We go over to that line here, and we can go up to the temperature line up here, and it says we need a temperature of about 275 C in order to get zinc to give us the vapor pressure that we want. Notice the melting temperature for zinc is much, much higher, up over 400 C. And so in the case of zinc, we're not going to melt the material in order to get the vapor pressure that we want. That's really, really nice. That means that the zinc will likely not attack our boats. We won't get some sort of violent reaction between the zinc metal, for example, in our tungsten boat. As I mentioned, typically for thermal and e-beam evaporation, you want a vapor pressure somewhere in the 10 to the minus 2 to 10 to the minus 4 range here. Much below 10 to the minus 4, you're not going to be able to read much of a deposition rate on your quartz crystal microbalance. And so think about being in this range here. Now, different materials need different temperatures. And so here I'm showing you two different materials, magnesium and aluminum. Both have very, very similar melting temperatures, but just notice that for magnesium, if I want a vapor pressure of 10 to the minus 3 torr, I only have to heat my magnesium up to 385 C. So that's pretty neat. We won't be melting the magnesium, but for aluminum, because the intermolecular bonds on aluminum are so much stronger than what we see with magnesium, in order to get that same equilibrium vapor pressure, I've got to heat the aluminum up way above its melting temperature. So it's just going to melt about 660 C or so. So the aluminum is going to be molten. It's going to be very aggressive. It's going to try to drill holes through your boats or your crucibles. Aluminum is just really, really a nasty material to work with. We've got a guy on staff named Rob Bellin, and he's a really walking book of useful knowledge on e-beam and thermal evaporation, and he kind of provided me with a couple little tips here for the materials that you're working with. In terms of trying to choose a boat to use, Rob's suggesting tungsten and tantalum for things that are going to sublime. For things that are going to melt, that's just a nightmare. If you've got molten material in your chamber, it's just really, really risky. Copper's not such a bad actor for things like that. If you do want to deposit gold or palladium or nickel, there's boats out there that are coated with a ceramic, aluminum oxide, to try to keep these metals from attacking your boat. If you're trying to do titanium, Rob suggested that you just use something that's cheap, because you're going to be throwing it away about every application. Things like silicon have got some really, really strange behaviors, and so he's just saying his coaching is good luck on that. And again, if you want to do organics, we've got these really, really wonderful low temperature evaporation boats that you can use. Now, we have tried to summarize all this stuff for you. We have a thing called the materials deposition chart, and that's available on our website. If you want a hard copy of this, let me know, send me an email, or send Nate or one of your contacts at the university an email on this, and we'll send you either a lab notebook if you want, which has this chart in it, or a big wall poster. If you've got a big crack in your wall or something you're trying to cover up, the wall poster is pretty handy for that. But what we tried to do now is take all of the deposition information that we have for oxides, for nitrides, selenides, sulfides, all this stuff, and put it into one big chart for you. And so if we would look at aluminum oxide as an example here, we're giving you the chemical formula, we're giving you the melting temperature, we're giving you the theoretical density, which you're going to need for a calculation I'm going to show you in a second. And we're saying for thermal evaporation, if you want a equilibrium vapor pressure of 10 to the minus 4 torr, you need to heat aluminum oxide up to 1550 C. Boom. There's your answer for that. We're saying it's excellent for e-beam evaporation. We're saying if you do want to do thermal evaporation, we're recommending a tungsten boat for you. Now, that doesn't mean your tungsten boat's going to last forever. We're just saying that that's the best choice out of a bunch of bad choices for these boats. So the tungsten's better than tantalum, better than molybdenum, but none of this is going to last forever. If you do want to sputter it, we're saying because it's a dead insulator, you're going to have to sputter it by radio frequency. We'll talk more about that in a little while. Or you can sputter it by reactive deposition, where you can sputter an aluminum target in the background of oxygen and make aluminum oxide. I'll talk more about that in a little bit. Again, so we tried to give you all the information that we could assemble for everything we could think to deposit. Generally speaking, most of the information is correct. There may be a couple of typos or something in there, but we do try to update it once a year. So again, thermal evaporation is great for a lot of single elements. As long as you know the temperature you need to get to based on the vapor pressure that you want. It's not good for alloys or elemental mixtures because these things tend to have different equilibrium vapor pressures. And so if you wanted a mixture of something like nickel and bismuth, for example, the vapor pressure of bismuth is much higher than nickel, and so it's going to evaporate preferentially, and you won't get the stoichiometry that you want. The stoichiometry of your source material will be very different than the stoichiometry of the film. Now, there are some materials, let's say like nickel and chrome, where their equilibrium vapor pressures are very similar, so you can kind of get away with it that way. So again, just look at that chart that we talked about and make sure if you do want to do some kind of mixture that the equilibrium vapor pressures are very, very close. Again, now with thermal evaporation, you know, if you've done any kind of coating of things with parylene, you know, again, that's thermal evaporation of an organic. If you're doing any of this perovskite solar cell work, they're using with ALQ3 again. So it's all done pretty nicely, but at very, very low temperatures. I mentioned base pressure. Again, that's just really, really critical. You've got to know what base pressure your system can get to. The lower in pressure you can go, the more pristine the films are that you're going to make. If you want to make two films that are identical in two different depositions, you've got to be able to get back to that same base pressure every time. So it's really critical that you know the system, the pressure your system can get to, and that you can keep your system clean and pristine, and don't ever get in there with your bare hands and leave a fingerprint. A fingerprint can cost you a decade on pressure. And certainly, if you're working with reactive materials like aluminum or niobium or titanium, again, if you've got any extra oxygen in your system, you won't form the metal that you want. You'll form some kind of an oxide. Now, we always recommend that you do some kind of a ramp and soak procedure when you're trying to do a thermal or E-beam evaporation. Where you've got an initial ramp and soak up to a temperature hot enough that you can desorb all the water and fingerprints and junk off your system. Maybe you do this with your shutters closed, and maybe a second ramp and soak, maybe with your shutters open, where you're trying to look at your quartz crystal microbalance and see how your deposition rate is increasing, and then a final short little ramp up to the desired rate that you need. Again, you never want to use more power than you need. There's no reason to go to a deposition rate or an equilibrium vapor pressure over 10 to the minus 2 torr. You will not like the morphologies of the films that you get. We do recommend calibration runs. And so if you're starting over with a new boat, if you're starting over with a new material, you do a calibration run. Do something onto a microscope slide, something that's not onto your precious substrates, just so you can look for melting temperatures. You can look for reactions between the material you're depositing and the boat. It'll let you set the tooling factor for your quartz crystal microbalance. Again, your quartz crystal microbalance needs to be educated about what material you're using, and by doing a calibration run, you can generate this thing called a tooling factor. I don't have time to go into that just yet, but again, your quartz crystal microbalance is going to have some kind of a readout that's going to be out in the control panel for your system. The quartz crystal sits down in here in a water-cooled holder in order to keep that crystal at the same temperature. As you deposit material, the crystal has got sort of a natural vibration that it does, and as you deposit materials on it, you're going to change that vibration, change that frequency, and we'll use that change in frequency as our proxy for deposition rate. So it's got some kind of a natural frequency that it vibrates at. As we deposit more material on it, you can see that frequency again is going to just drop and drop and drop, and we can use that change in frequency as our proxy for deposition on the films. Now, the position of where you put that quartz crystal microbalance is kind of critical in your system. So if you're using two heads, for example, and you've got one maybe up near your substrate, which is a great location, and maybe a secondary one here, just notice that as you dig down in your material, and this would be maybe more relevant for things like E-beam, for example, you may eventually get to where that flux is no longer impinging on that quartz crystal monitor. So just be really, really mindful when you place these things in your system that they're close to your substrate, so they're going to see that vapor flux throughout the deposition here. Now, I mentioned film thickness. I mean, obviously, before you make a film, you should know how thick the film is that you're trying to make. I love thermal evaporation because it's really kind of the most material efficient technique that we have here to make a thin film, so that if we know the source to substrate distance, and we can use that to calculate the area of a hemisphere, and we can do some math there to figure out exactly how much material to put in our system. So here's an example for you. And so if we know the source to substrate distance is 20 centimeters, we can use that to calculate the area of a hemisphere. If we know the thickness of the film that we want to deposit, in this case a micron film, we can calculate the volume that we would need to coat that hemisphere with a 1 micron thick film. And using the theoretical density of the material that we're depositing, we can calculate exactly how many grams we need to put into our boat in order to make that 1 micron film. Now, our experts would tell you probably you want to add in a little bit of a safety factor. Maybe 20% is a little heavy for gold. Maybe you want to put in an extra 10% in order to make sure that you get your 1 micron film. Now, this calculator is available on our website. And so if you go into the website and go to evaporation materials, this calculator will pop up, and it'll let you input the source to substrate distance. You can either tell it you're doing gold, or you can type in the theoretical density of the material if it's not already on our list. And it'll prompt you for a safety factor. And so you can go without it if you're feeling pretty courageous, or you can put in 10% or 20% of that, and it'll actually calculate how many grams you need to do that deposition. Now, as I mentioned, these boats are consumables, and they get attacked pretty readily by molten materials. I think this is a tungsten boat that maybe had aluminum in it, and you can see that the molten aluminum ate a hole through the boat after a certain number of depositions, caused a crack there again. So these things are consumables. Just know that when you buy them, I think we sell them in packs of 6 or 12 or something like that. We think that you're going to get a deposition or maybe a few depositions out of them before you got to change them. Now, if you're using crucibles, those are probably going to give you a little bit more life, but just know, again, this is titanium in an aluminum oxide crucible, that after heating for a while, if the titanium happens to wet to the ceramic, after you cycle it a few times, you're going to have maybe some cracking. The coefficient of thermal expansion between the titanium and the aluminum is such that it's going to eventually stress that boat out, or that crucible out, and you're going to crack it. Once you crack it, you're going to have molten titanium running around your vacuum system, and that's considered bad. So don't do that. Keep an eye on your crucibles, and so you don't crack them or don't put holes in them and leak molten metal all over your system. I mentioned that the voltage and the amperage that your power supply can generate, that completely dictates the suite of materials that you can make by thermal evaporation. So if we would look at this first item here, and I think this is a screenshot out of our catalog or the RD Mathis catalog. This is a 5/1000th of an inch thick molybdenum boat. And just notice that if I give it 2.1 volts and 198 amps, this thing will go to 1400 C. How clever is that? So if we think back about our example of aluminum oxide, remember that wanted 1550 C in order to give us the equilibrium vapor pressure that we wanted. So 1400 C is not going to do it. Here's a 5/1000th of an inch thick tantalum boat, 1600 C, kind of too close. I wouldn't really use that one. If we drop down one more though, this 5/1000th of an inch thick tungsten boat, if my power supply can give me 4.3 volts and 316 amps, that boat will go to 1800 C. So that's well over where I need to be in terms of the 1550 I'm trying to generate. So that's probably a decent choice to do aluminum oxide. Now, After I do one deposition or so and my boat cracks and I'm all upset about that, you call the Lesker company and the person on the phone is going to say, hey, use a thicker boat. So go for a 10,000th of an inch thick tungsten boat. But notice now the requirements for your power supply have changed. So now it's 3.3 volts. It's 451 amps in order to get you that same 1800 C. So just be really mindful about what your power supply can do. That will completely dictate the suite of materials you can do by thermal evaporation. Just to wrap up on thermal, again, we're going to use these wonderful refractory metal boats. We can use crucibles if we want to. There's lots of options there. Generally speaking, we're going to evaporate up. Again, I want you to know the parameters of your power supply so you can know what materials, what temperatures you can get to. In terms of chamber pressure, I want you to go as low as you can possibly go. So I put 10 to the minus 8 torr in there. Hopefully your systems will go to that pressure. But again, just keep in mind that whatever pressure you can go to, make sure you can get to that same number over and over and over again. The thermal load on your substrates can be high if you're depositing for long periods of time. I'll show you some examples of that in a little bit. Now, let me talk quickly about E-beam evaporation. Again, most of the comments I said by thermal will apply to E-beam, but there'll be a couple other things I need to point out here. Hey, just know that E-beam evaporation may be one of the more complicated techniques out there that you'll ever use. There's lots of black art going on there. I highly encourage you to send questions to us if you're going to go do E-beam and for a material that you don't have a process for. We've got lots of experience there. So for those of you that haven't done E-beam, this is a cartoon, a sideways cross section of an E-beam boat or gun. It's typically a big honking block of copper. The copper, again, is going to be water cooled because the E-beam gun gets enormously hot. In the front of the gun, we've got a filament, typically going to be tungsten. The tungsten, when it's energized, will go to 2,700 Kelvin. That's hot. We're going to use magnets in the gun to bend that stream of thermionic electrons over to our source material. And when it hits our source material, we're going to generate this wonderful vapor plume. Again, enormous amounts of heat here. Now we can focus and defocus the beam. We can use magnets to drive the beam around the gun. Again, very, very energetic process. Now we can do anything. Now we're not particularly nervous about tungsten or titanium or platinum. We can make a film out of anything. Here's a couple of new guns. Again, in your career, it's unlikely you'll ever see them as clean as this. This is a single pocket gun here. The filament I talked about, you can just barely see right there. I'll show you a better image in a little bit. This is a multi-pocket gun. And so here you can see one pocket here, but there's maybe 5 other pockets back underneath this cover here. And so if you've got a multi-user fab and people want to do different kinds of materials, we can put silver, gold, platinum, titanium, tungsten, all these various pockets, and then rotate that carousel around. We would want to do different materials, or if you've got one material and you want to do layers and layers of it, we can fill it all with the same stuff and rotate it around. Hey, just be mindful if you use one of these multi-pocket guns that as you change materials, you're typically redepositing material on that lip there. And over time, if you don't clean that lip off, film will build up, it'll flake off and fall into your crucible, and then you're depositing some kind of a crazy weird alloy. Very, very tough to duplicate those results. Again, used widely in industry. And so if you use, most of your optical lenses are coated by E-beam deposition with maybe an ion support or an ion assist. Your thermal imaging lenses, things like that, are all done by E-beam evaporation. So getting good at E-beam is definitely a full employment program for everybody. Now, again, I can't say enough about cleanliness. You've got to keep the chamber clean. You've got to keep your sources clean. You want to try to use high purity materials, and so you don't kind of have mysterious elemental impurities in there. Again, and if you don't know, if you've got questions, just, get a hold of me or get a hold of our, use our tech info service and get you an answer there. Again, we don't use any heaters in E-beam. We're just going to use the E-beam itself. We use magnets in the gun to bend it 270 degrees. You can E-beam off the bare hearth. I'm not a huge fan of that, but if you're courageous, you can do that. Or you can pick a crucible. And typically, if you want to do conductive materials, you've got to use a conductive crucible, like copper or tungsten or pyrolytic graphite. We're going to always E-beam up. The power supply parameter is a little bit different here. Your evaporation rates are massive, but you don't have much control over it. Again, I want you to go to the lowest possible pressure you can achieve in your system. And again, you get to the lowest numbers when the system is clean. So please try to keep your systems really, really clean. And again, your thermal load now on your substrates is really, really high. And so if you're trying to do film through PMMA, or if you're trying to use organic substrates like cellulose, you got to be really, really mindful of the temperatures you're going to get to. Question here is, do you want to sweep the beam around? So here's an image done with an optical filter, so you can see this E-beam, you can see it hitting your source, you can see the flux coming off there, and the question is, do you want to move that beam around during deposition? And if you've got something which does not have great thermal conductivity, like a ceramic, or maybe metal targets that are made from powders like chrome, you may want to sweep the beam around. If you've got things which have got better thermal conductivity, like titanium, maybe you don't necessarily need to sweep the beam. But again, there's lots of black art here, and I would encourage you, if you don't have an existing process, to please engage us or some other expert on how to do this properly. And your E-beam sweeps can be really fancy things like this, or they could be spiral shaped genes. I mean, there's all kinds of sweeping you can do. We don't have time to kind of go into the details just yet. But again, I do want you to pre-melt those metals. And so if you start out with pellets, I would prefer that you pre-melt those things into one solid chunk before you actually do your deposition. Generally speaking, you would like the surface of the material that you're depositing to be pretty flat. If you've got big peaks and valleys there and you're sweeping the beam around, you're going to be changing the shape of your flux pretty frequently. Here's an example. Here's of somebody who actually core drilled through the material into the gun. So these are molybdenum oxide or molybdenum pellets here. He didn't pre-melt them to make one solid slug. You can see the pellets off here because he wasn't sweeping the beam, didn't even get molten at all. And so he E-beamed through the material, E-beamed through the crucible, E-beamed through the copper hearth, and hit the water cooling jacket. And when he did that, the E-beam system filled up like a washing machine. That's considered bad. Don't do that. That will really mess with your day. Other things that go weird on these crucibles, again, if you're doing things like silicon, silicon tends to grow up out of the crucible in the direction of the beam. I can't tell you right now why it does that, but it does. Very, very crazy. If you do have a material which has gotten molten in your crucible, after a few cycles, it will crack the crucible. And once it cracks the crucible, you'll notice you'll need more and more and more power to do your deposition, because some of your metal in the crucible is actually in direct contact with the water cooling jacket. Don't overfill your crucibles. If you overfill them, let's say more than 2/3 full, as that material gets molten, it will crawl out of the crucible and attack the gun. That's considered bad. Make sure you don't have any junk laying down in the pocket of your gun. So here's a gun where somebody left a pellet down below, and then when they put their crucible in, obviously the crucible wouldn't sit flat, and they got some very, very strange behavior. So just be mindful of that. Know also, again, the heat's coming in from your E-beam, and you're hoping that it goes out the crucible for some material. So just be mindful about the heat flows in your E-beam system. Now, for some materials, like platinum and tungsten, maybe tantalum, you may not want your crucible to be in direct contact with a water cooling hearth. So maybe you'll put a small washer down here of graphite or something like that, so that the crucible rests up on top of that washer, and you're not water cooling the crucible. For other things like aluminum is so horrible, you do want it to be in complete contact with the water cooled gun, so that we can keep the aluminum cool and it doesn't spit. Now, I talked about heat load before. Again, these are images from Case Western Reserve University. When they were trying to do contact pads on a microscope slide with a plastic mask by E-beam, you can see that they actually made some decent pads here. Everything looked great. Then they tried to use a paper mask, and the heat load on the paper mask was way more than the paper could handle. It outgassed a lot, and so they formed things like silver oxide here. The paper warped, and so they got maybe no films formed at all, or very, very horrible resolution there. Again, this is heating with E-beam is really, really tricky. So if you're using paper mass, you got to be careful. If you're trying to use PMMA, which may have an upper heating temperature of 90 C, or organic substrates, again, be really, really mindful with E-beam. Now, there's some things we can do, like increase the throw distance. And so if you've got enough head height in your E-beam system, maybe you can increase the distance between the source and your substrate. Again, in this case, if you can add 3 inches to that throw distance, you can drop the heat transfer load by maybe 30% or so. Again, there's a couple tricks you can do if you've got a heating issue. Again, I just mentioned these charging effects. So if you're trying to do an electrically conductive material like a tungsten or a tantalum, don't put it in an aluminum oxide crucible. If you do, when the aluminum oxide crucible charges up, it will start to deflect the beam. And so now the beam won't hit your source material, but it'll hit the gun. And so you'll be depositing the gun. And again, that's considered bad. So just to wrap up on this, again, E-beam is great for elements. Now we can do anything. All of your wonderful refractory metals, even platinum and things like that. We still have a challenge with mixtures and alloys. You've got to be mindful about the equilibrium vapor pressure. Make sure that they're matched. If they're not, then you're probably going to have to do some co-depositions, for example. Really no organics possible here, way too much heat. You've got an issue with things disassociating too. Really not good for low temperature materials at all. Again, I still like calibration runs. Again, I want you to use electrically conductive crucibles for the most part. Don't overfill your pockets, because the material, if it melts, will get out of the crucible. Don't use too much power. If you use more power, it'll ruin your boat sooner. What else? Things that go wrong. Typically, it's related to the filament not being aligned properly. I'll show you an image in a second. Core drilling. If you don't move your beam around, you're likely to core drill through your crucible into your materials. Bad, bad, bad. If you don't keep your multi-pocket gun clean, you're going to have cross-contamination issues there. And then I mentioned this charging effect. You've got to use electrically conductive crucibles with electrically conductive materials. Oh, here's the image. So if you have trouble with your E-beam gun, I want you to break vacuum, take out your smartphone, and take this picture and send it to me. Here's an image of this filament here. Notice this one's in there nicely. You're only seeing half the filament. The other half of the filament is up in the top of the gun here. If everything's great, this is going to be parallel, nicely aligned with this. If things have gone wrong, if you've got an old filament, for example, you might see something that's swayed like an old horse. Maybe the filament's in at a bad angle. I think with our guns, we actually give you a little plastic, a little plastic fixture to go in here to keep this nice and parallel. Anyway, just be really, really mindful and try to keep all this clean. The cleaner this is, the fewer issues you're going to have and the lower pressures you can get to. Okay, let's go ahead and take a 5-minute break, and then when we get back, we'll talk about sputtering.
All right, before everybody leaves for the break, I just want to remind everyone that JR is presenting by arrangement with Giant Fab, the core facility that's up on the 4th floor of Tech J-Wing. We're a core facility. We have 2 different evaporators. We have a thermal evaporator for metals that uses the boats he talked about, and then we have a low temperature evaporator that's suitable for organics. So a lot of you know about Giant Fab, but if you don't, you can go to giantfab.northwestern.edu and you can find out more about us. We're definitely looking for new projects, so come to us with your vapor deposition projects. We also have spin coating and conductance and photovoltaics testing capabilities all in a glove box train, so you can load your substrates in, do wet chemistry on them, do evaporation on them, and then do electrical testing on them without ever taking them out of the inert environment. So again, that's giantfab.northwestern.edu.
Okay, great. So let's take a 5-minute break. I'm going to time you. So in 5 minutes, I'm going to start talking again. I can't see whether you're in the room or not, but again, take 5 minutes. I'll see you. the way down. Okay, campers. Hopefully everybody is back. I can't see you. I just assume that you've come back. Okay, I'm going to get started. Again, let's talk about sputtering for a while. It's a really, really lovely thin film deposition technique. Let's see if I can get my system to go. Okay, so here's a sputter system. Again, these are much more complicated than your thermal or E-beam systems. You know, now we can bias the source material, we can bias the substrate, we can have a variety of power supplies, and we can sputter insulators, we can sputter things that are electrically conductive, we can do pulse deposition. Again, lots more things going on in sputtering, and this complexity is a little hard to grasp, but it just gives you much more control over the morphology of the films that you deposit. Here's the interior of that system. Again, this is in what's called a D-shaped chamber. So unlike that thermal system I showed you earlier, this chamber here has been manufactured, so we've kind of eliminated the corners that you would have in a normal box chamber. That makes it a little bit more efficient in terms of pumping. Maybe this one's been electropolished on the inside, so it's a little easier to clean. This happens to be a 3-gun system, so there's a gun here, there's one back here, there's another one over here. Sputtering is a wonderful technology. So in this case, I'm showing you guns that are pointed up, but with sputtering, I can sputter sideways, I can sputter down. I may show you an example here of a sputter cathode on a robotic arm so that I can move the cathode in real time while I'm depositing films. So it's just a wonderfully flexible technology. Again, you know, in this case here, I've got my cathodes down low, my substrate are on a carousel up here, which is going to rotate. I've got 2 different quartz crystal microbalances. Again, a very flexible system. Now, this is an older system. Typically, I don't like cathodes kind of being grouped this tightly together. You know, like I said, with thermal evaporation, everything contaminates everything. So again, the further you can get these things apart, or if you can get newer cathodes built on tilts where we can tilt these things away from each other, you'll have a fewer issues with cross-contamination and maybe even easier to clean. Here's a giant sputter deposition system. And so this is a system which is built for architectural glass. I mean, it's sort of a city block long. This thing will take in a 10-foot by 10-foot piece of glass, take it through a series of load locks in real time, and then into the deposition chamber. There's 27 cathodes in this deposition chamber. Each chamber or each cathode is 13 inches wide by 13 feet long. These cathodes are so massive, it takes this crane to lift them in and out of the deposition system. So here's a couple of people in here just for scale. Here's a couple of ghosts, probably guys that were killed on the job that have come back to haunt these guys because maybe they weren't great managers. But again, just really, really massive systems. And this system will process one piece of glass sort of every 30 seconds and put 7 different layers of metal on one side of that piece of glass. Unbelievable systems. Now, so in magnetron sputtering, again, we've got our substrate, and remember the substrate is what? It's clean, it's pristine, it's never been touched by human hands. Remember, I'm sure none of you have ever touched anything going into your vacuum chambers with your bare hands, right? Raise your hand if you've touched something going into your system with the bare hand. Now, so you've got your substrate here, you've got your target here. Now, but with magnetron sputtering, we actually have magnets back behind the target, and this is really ingenious. And so notice that my center magnet here is a north pole, south pole. The side magnets are south pole, north pole. So on the face of the target now, I've created a sort of a magnetic field here. And that magnetic field is going to be really handy here in just a minute. So I'm going to introduce a process gas. Typically, it's going to be argon, but we can do this with krypton or xenon. I'll show you some data on krypton in a little while. We're going to generate a stream of electrons, and those electrons are going to be captured at the surface of the target by this magnetic field. We're going to use those electrons to ionize some of this argon gas. Those argon ions are going to crash into the surface of the target and then physically eject out a target material, which is going to come out at a bunch of strange different angles. We'll talk about that more in a little bit. And hopefully those atoms then will hit the substrate and will form the film that we want. And hopefully that film then will have the properties that we want. And if it doesn't, hopefully there's some kind of post-deposition process we can do to get the properties that we want. Now, just a little more detail here. So here's our argon ion that we created with our collisions of these electrons that we generated and our argon atoms. And this argon ion is going to crash into the surface of the target, and based on the energy that it has, and we have some control over that energy by how much we bias the target itself. If everything goes well, that ion is going to crash into the surface of the target, and we're going to eject a sputter target atom or molecule, which is going to go up there and become part of our coating. Now, based on the amount of energy here, if we don't have a lot of energy as this ion crashes into the target, it may simply just bounce off the surface and we won't get any sputtering. If the energy of that ion is, let's say, under 1,000 EV, that ion is likely to do its job, crash into the target, and physically knock a sputter target atom out. If it's more than 1,000 EV, there's a possibility that that argon ion is going to penetrate and embed itself into the body of the target. And if it does that, it's going to start to charge the target. And if the target itself is an electrical conductor, like a metal, that's not going to be an issue. We can shunt that charge away. If it's a ceramic, then we have an issue. And so we'll talk more about that in a while. But as an artifact of this collision, as an artifact of this thing crashing into the target, we're going to create some secondary ions. Actually, that's not true. As a part of ionizing the argon, we're going to create some secondary ions. And those secondary ions are going to be trapped by that magnetic field at the surface of our target. They're going to continue to rotate around that surface and help us create more argon ions. Now, remember, with thermal and E-beam evaporation, we're going to get our atom flux by heating things. And sputtering, we're going to do it through these collisions of ions with the surface of our target. And because we have magnets involved, we've got to keep our targets cool. So again, with thermal evaporation, we're trying to get things hot. With sputtering, we're trying to keep things cool. And typically, we're going to cool things with water. And so this happens to be a direct cool target. So I've removed a part of the sputtering target so you can see the water cooling channels that sit back behind the metal target. So this is a very efficient technique. It's called direct cooling. The small research cathodes that you're working with are indirectly cooled. And that means I've got water coming up through the stem here and flowing against the backside of this copper plate. And then my sputter target goes in on top of that copper plate. So now I've injected a thermal interface there. And so these research targets are a little bit tougher to keep cold. You got to be really, really mindful about the cooling water in these systems. So again, sputtering now we're doing all kinds of wild stuff. We're combining things like plasma physics, and we're going to do some chemistry. If we're going to do reactive sputtering, for example, we're going to do material science and even electrical engineering. All of this stuff goes into the sputtering process. And so here's just a cartoon of a sputtering cathode. And so here we've got the sputter target here, and this is going to be called the cathode part of the target. And then we've got the anode, which is in this case embedded in the thing called the dark space shield. And so we're actually going to create electrons right in this gap between the anode and the cathode. And the size of that gap is really, really critical. And for most cathodes, it's designed to be about 80 thousandths of an inch. Over time, if you've done a lot of aggressive cleaning and things like that, you may have changed the dimensions on that gap, which are going to affect the performance of your gun. Again, we're going to use our magnets in the gun to create this magnetic field at the surface of the target, and that's going to be the trap for the secondary ions that we're going to generate during the sputtering process. Again, and there's our water cooling lines that are come up in here, and they're probably going to flow water around the magnets and then out. Again, as I mentioned, we've got electrons flowing everywhere. They're going to collide with those argon atoms that we eject into the system and create argon ions. And then as an artifact of that collision, we're going to have some secondary electrons flowing around in the chamber, which we're going to try to capture in the magnetic field at the surface of the target. This plasma that we generate is really a mixture of ions and electrons. That mixture is wonderfully neutral. So the plasma itself does not have an electric charge, but it is electrically conductive. And because it's electrically conductive, we can affect the shape of that plasma with magnetic fields. And I'll show you how we do that here in a little bit. Now again, sputter systems are typically not designed to go down to very low pressures. And so typically 10 to the minus 6 or 10 to the minus 7 torr is a reasonable base pressure for a sputter system, because we're going to backfill with a bunch of process gas and operate at a pressure more like 100 millitorr or so. Now, if you are doing reactive materials, magnetoresistive materials, if you're doing superconductors, if you're trying to do pristine aluminum films or titanium films, it may behoove you to pump down into ultra high vacuum to get rid of oxygen, to get rid of water or minimize water, so that those things are out of your system so that you can make a more pristine film. I'll show you some examples of that in a minute. Again, if you're trying to make, let's say, niobium superconductive films for use in qubits, if you get any gas inclusions from oxygen or water in your system, you're just going to make horrible niobium films, which are going to be really, really sloppy qubits, and qubits are already moody anyway, so you'll need to make a great film. What else I want to tell you? Okay. Now, here's just a cartoon for you. Now, I flipped the whole thing around now. So the target's up on top. The substrate now is down at the bottom. And I just want to show you that within this magnetic field that we have at the surface of our target, we have a real mixed bag of things. And so we've got these white spheres are going to be electrons. So we have swarms of electrons that are trapped at the surface of the target. We've got argon atoms, these yellow things, which get into the flow of those electrons and get ionized. So we have argon ions again, and we're going to negatively bias our substrate so that the argon ions are attracted to collide into the substrate. And then we have target atoms coming out. But because we have only a tiny fraction of the argon gas that we generate or that we inject in the system gets ionized. And so we have an enormous amount of argon gas in our chambers that are just along for the ride. And unfortunately, some of this argon gas is going to get included in our films, and it's going to cause us some very, very strange film growth in some instances. So again, I just wanted to detail for you this mixed bag of atoms, ions, and electrons that we have in our sputter, right around the surface of our sputter cathode. As I mentioned, we talked about mean free path earlier. Again, at 10 to the minus 3 torr, your mean free path is on the order of 4 inches. If we go up a decade in pressure, we go down a decade on mean free path, so that the film you make at 10 to the minus 2 torr is going to be very different than the film that you make at 10 to the minus 3 torr. And here's some examples. So these are both copper. Over here we have copper at 10 to the minus 2 torr, and you can see very columnar, not very dense, not a great film example. And then if we go down a decade in pressure, though, that mean free path is increased substantially. Now we make essentially an amorphous, dense film. The arriving atoms have much more energy. They can move around and fill in spaces and actually make a great film. I mentioned before that the atoms coming out of our sputter target are coming off at a lot of crazy angles. Again, you've got to use sort of this cosine rule that was really kind of developed, or at least discovered or published back in the 1890s, so that the most probable pathway for one of these atoms leaving your sputter target is normal to the target face, but there's pretty high probabilities for all of these other angles. And so with sputtering, we really don't have a whole lot of control over the direction that these atoms are taking as they leave our target and head toward our substrate. And there's a couple other reasons for that. Now, you think back about evaporation. Remember, with evaporation, I told you we're going to work at the lowest possible pressure we can achieve. And because of that, we're not going to have very many tramp molecules in here. We're going to have huge mean free paths, and that our atoms then are going to arrive sort of normal to our substrate. We're going to have nice, pure, clean vectors on those things, and they're not going to get knocked off course by any tramp gases in our system. If you look at sputtering, though, with sputtering, we have got things coming off the target itself at strange angles, and then we've got all that extra process gas in the system where these atoms are going to collide with that and get even crazier angles coming off our sputter cathode. And so if you think about trying to, let's say, evaporate through a mask, so if we've got a mask here, and we've got our incoming atoms coming in sort of normal to that substrate itself, we can make some fairly crisp structures here at the surface of our substrate. Whereas with sputtering, where we've got these atoms coming in at all kinds of rakish angles here, we don't get very good resolution with respect to our mask, and so we get some pretty fuzzy looking depositions there. Now, notice also that a lot of your substrate holders are going to have your substrate at some kind of angle relative to these incoming atoms. And that is so that we can have to do some what's called atomic level peening here. So if we had our atoms just coming in normal to the substrate, generally speaking, they're going to sort of stick wherever they land. They're not going to move around very much, and so you're going to end up with some voids in your film. Whereas if we have atoms coming in at some kind of an angle, each atom that comes in is going to peen, it's going to bonk into an existing atom and kind of move it around a little bit. And by doing that, we can have a sort of improved density on our films. Now, we got magnetic fields involved here. That means we've got a lot of mysterious things going on. This is Magneto. He was either a superhero or supervillain. Maybe some of you can fill me in on that later after the talk. But if we look at these magnet configurations, this is what's called a balanced magnetron. So now all of these magnets have the same magnetic strength, and because of that, we have sort of a nice uniform magnetic fields at the surface of our substrate. Again, in this case here, we have a central magnet here, and then we've got a ring magnet on the outside. You'll see lots of different magnet designs if you take apart people's cathodes. In this case, this particular designer was doing them with bar magnets. So we've got lots of options there, and there's a lot of intellectual property invested in the design of these magnetic fields. So here's a cartoon again, which just shows you the center magnet here, a ring magnet on the outside. There's our magnetic field at the surface of the target. And I think that if this is a North Pole, South Pole, and this is South Pole, North Pole, that our electrons are generally speaking going to flow this direction. If you don't like that direction, we can flip those poles around and we can get the electrons to flow this direction. As I talk to my colleagues in the industry, I can't get anybody to argue with me about whether it matters, whether they go this way or go that way. So I don't think there's going to be any Nobel Prize awarded for that one. If we want to image the flow of these electrons, though, it's really fascinating. So these things are not just simply rotating, they're actually going back and forth and back and forth and back and forth. They're actually going up and down and up and down and up and down. And so you can see that the electrons at the very top edge of that magnetic containment field are moving very quickly on the order of 2,600 meters per second. Whereas the electrons down at the face of the target are not moving nearly as fast. And so they've got this kind of I don't want to call it a spiral action, but it's back and forth and it's up and down. It's really quite active. Wonderful imaging here. This is done, David Ruzik's group. I think Priya did a lot of the imaging at the University of Illinois. Now, we can also have what's called unbalanced magnetrons. And so this is a balanced magnetron here where we've got sort of nice uniform fields over the surface of our target. But if we have a substrate, for example, where we do not want to have a lot of sort of aggressive ionic bombardment, we can have an unbalanced magnetron where we have a stronger center magnet than we do in the sides. And so we can bend those magnetic fields out this way. And so we can affect the pathways of these ions away from our substrate. If we do want our substrate to be bombarded by ions, we can reverse the unbalance there and have stronger fields on the outside than we do on the inside. And we can have these magnetic lines actually impinge on the substrate itself, and so that the species that arrive at the substrate are much more energetic, and we're most likely to get a more dense film. Again, just pretty pictures here, just showing you an unbalanced magnetron where those magnetic field lines are going to impinge on our substrate, and by doing that, we can, we can affect the density of the films that we grow. Now, I talked about substrate manipulation. Just keep in mind that if we had a substrate sitting up here in a fixed position over the surface of our sputter target, if we look at a property like resistivity, we may have big changes in resistivity. If this is the center line of our substrate and our target, from the inside out to the edges, where we might see a drop in resistivity here in the sputter target or sputter track, and as we get out toward the edge, maybe an increase in resistivity. So again, it's pretty important for a lot of reasons to be able to manipulate your substrate through these plasmas during deposition. Now, as I mentioned before, we can use electrical biases. We can negatively bias the substrate here so it's more attractive to these argon ions, so we can speed them up. We can add more energy to that collision. We can also positively bias our substrates so that they're more attractive to these add atoms that are coming from the target to the substrate itself. And so we can use the bias of the substrate, for example, to affect the stresses in the films that we deposit. And so we can use those biases to have our films be under a lot of stress, or we can minimize those biases to be under not much stress. We'll talk more about that in a little bit. We can also do what's called reactive sputtering. And so keep in mind that your deposition rates for things like metals are typically much higher than what you get from oxides or nitrides, so that if you want high deposition rates and you also want to make, let's say, an oxide coating, you can do what's called reactive sputtering. So I can sputter from, let's say, a titanium metal target or an aluminum metal target. I can introduce my argon process gas, but also add some oxygen into that gas stream, so that I'm going to have my argon ions collide with the target, eject metal atoms or molecules there, but then they're going to collide with the oxygen that's in the system, and we'll do a little bit of chemistry, and by the time we get to our substrate here, we're actually depositing an oxide. I make that sound real simple. It's not simple at all. There's lots of levers and knobs to pull so that you get the stoichiometry that you want, that you do the proper amount of chemistry in the course of injecting a reactive gas in that plasma so you get the stoichiometry of the film you want. Again, lots of tricks to do this. Just as some examples for you, I mentioned titanium. So if we want to make titanium nitride, for example, we can sputter titanium metal in the presence of argon and nitrogen to make titanium nitride. Similarly, we can do aluminum nitride the same way, or aluminum oxide, where we're going to have argon as a process gas and mix in the reactive gas, either nitrogen or oxygen, to make either an oxide or aluminum nitride in this case. We can also do reactive sputtering by radio frequency. So if you've got an insulator, let's say lithium orthophosphate, which turns out to be a great electrolyte for a solid state battery, we can sputter that lithium orthophosphate in pure nitrogen gas, so no argon here. We'll crack that nitrogen gas in the process of doing our ionization, and we'll actually make a nitrogen doped lithium orthophosphate, which is a great conductor of ions for these solid state thin film batteries. If you're interested in solid state batteries, by the way, I'll be teaching a course at the SVC coming up in November on that battery technology. Now, as I mentioned, with reactive sputtering, we're very, very interested in getting the deposition rate that we get from metals and then also make a nitride. But one of the problems that we have in doing these types of deposition is a thing called target poisoning. And in target poisoning, what happens is we have a lot of kind of redeposition of, let's say, the titanium nitride material on the surface of the target itself, which turns that surface into a nitride instead of a metal. So let's say at relatively low nitrogen flow rates, low nitrogen partial pressures, we get the behavior that we want or the deposition rates that we want by sputtering a metal with a very, very minor redeposition of a nitride on the surface of the target. But as we increase that nitrogen flow, and we might have to do that in order to get the stoichiometry of the titanium nitride that you need, we get more and more redeposition of the nitride back on the surface of the target. So that, and notice the slope of this curve here, very, very tough to control on that slope. So if we get too much redeposition of the nitride on the surface of the target, now we're essentially sputtering a nitride. And so we don't get the benefits of the metal deposition rate that we want. There's a couple of really kind of nice sophisticated control mechanisms out there that we can use to control nitrogen flow rate so we don't see this transition. If we had more time, we'd chat about it. If you look at just deposition rate here on this axis here, just notice that we get the deposition rate that we want from metals, but then suddenly it collapses pretty dramatically to the deposition rate, let's say, of nitrides. Now, I mentioned water earlier. If you're trying to do things like titanium nitride and you've got water in your system, you're really kind of in trouble. Water, unfortunately, is a polar molecule, so it's got a kind of a positive side and a negative side, and so it tends to stick pretty well to the walls of your vacuum chamber, to the sides of your cathode. It's just really, really a pain. You've got to go through some fairly heroic things to get rid of water. And if it gets engaged in the plasma, we're going to crack that water. So then you're going to have things like atomic oxygen and atomic hydrogen in your system. Those are incredibly reactive, and they're going to want to add to your film. So if you're trying to make a titanium nitride, for example, and you've got a lot of water in your system, the negative free energy of formation prefers titanium oxide over titanium nitride. And so if you have a lot of oxygen in your system or a lot of water in your system, you're going to tend to form maybe things like titanium oxynitride. Maybe you'll get a mixture of these things. So in this case, it really behooves you to try to pump to a very, very, very low pressure to try to pump away as much of that oxygen, pump away as much of that water as you can. It also behooves you maybe to keep your chamber closed up and under vacuum when you're not using it, just to try to keep it from getting really, really wet. I mean, you can put hundreds and hundreds of layers of water on the walls of a vacuum chamber without really trying. Now, as I mentioned with sputtering, we're going to operate at fairly high pressures. That high pressure is going to cause you to have a lot of gas in the system, which is along for the ride. You're going to have a lot of collisions there, so your arriving atoms don't have a lot of energy to form a nice dense film, and your deposition rates are going to be pretty horrible, maybe less than 100 angstroms a minute. I just want to make a distinction between the things sputtering rate and deposition rate. So typically, when you talk about a sputtering rate, you're talking about the rate at which we're removing material from the target. And a deposition rate is the rate at which material is landing on your substrate. And unfortunately, a lot of authors use these two terms interchangeably, and they're not the same thing. So just be mindful of that when you're doing your reading. So as I mentioned, as we interject process gas into our system, only a tiny, tiny fraction of it actually gets ionized. And that's why we have to work at these really, really high pressures, because we're only able to ionize just a tiny, tiny amount of that process gas. And so if we want to think about a thing called the sputter yield, if we want to look at the ratio of the number of ions that actually hit the target and the number of target atoms that get relieved from the target here, that's a function of the mass of the material that we're sputtering. It's a mass of the incoming ion, and typically we're going to use argon, but I'll show you some data on krypton. It's a function of this bias voltage that we use to accelerate the ion to the face of the target itself, and it's a function of the ion's incident angle on the target. Again, your bias voltage will affect that a little bit. where high bias voltages tend to have the argon ion come in normal to the substrate, but normal to the substrate is really not necessarily great for sputtering. You want a little bit of an angle there. This thing called sputter yield is a kind of a function of the mass of the incoming ion. And typically we're going to use argon, which has got an atomic mass of around 40, but I'll show you some data on krypton too. So if you're not happy with your sputter yield, we can play around with which of these process gases we use and change that yield. Here's a bunch of different targets here. We've got carbon target, we've got aluminum, we've got chrome, nickel, silver, platinum. They all have a variety of atomic masses here. Carbon's pretty light, platinum's a beast. And again, if you look at our argon atom coming in, if we just look at the sort of ion to target atom ratios here, argon's 3 times the mass of carbon, but for every 1 argon ion that hits carbon, we get about 1.4 carbons out. Notice that for every 1 argon ion that hits chrome, we get about 12 chrome atoms out. And for platinum, we get about 8 out. So, it's not necessarily a linear relationship between these masses. If we're not happy though about our deposition or about our sputtering rate, we can go to a heavier ion. So we can go to krypton, which is roughly double argon, and you can see that we do see some slight increases in our sputter yields by going to a heavier ion. Although it's not linear. So, just notice we see, relatively kind of small increases by going to this much heavier ion. Maybe it's a little bit more linear when we look at things like platinum. Now, I don't know how many of you have bought krypton, but the last time I sold a bottle of krypton, I think 2,800 cubic feet went for about $8,000. And so much more expensive than argon. So if you really need to have it, you better have a budget for it. Now, another thing I'll just notice or note for you, for those of you that are trying to make, let's say, niobium superconductive films for qubits, niobium films, if you sputter them, tend to absorb a lot of argon gas. Argon is a little bit smaller than niobium, and it tends to just go right into that matrix. But if you graduate to krypton, krypton is much, much bigger, and so the krypton is not able to infiltrate that niobium metal film. So if you do want to make a great film for a qubit, you may be better off using krypton as your active gas. Different materials sputter at different rates. Silver sputters like crazy, copper sputters like crazy, wonderfully conductive. The intermolecular bonds are not too strong. Things like silicon dioxide, which is an insulator, we've got to sputter by radio frequency. And so, even over a wide range of powers, you never get a very reasonable deposition rate. So just notice that different materials sputter at different rates. I've got some comparison charts for you if you want them. I'm happy to provide them to you. Now, if you are interested in deposition rate, one neat trick is to change the throw distance. And so if we change our throw distance from our substrate to our target by a factor of 2, we're going to increase our deposition rate by a factor of 4. So this is a neat thing you can do. Now, there's some side effects, of course, of that. You may have some issues with film uniformity, film thickness, things like that. But if you're really, really dialed into deposition rate, one thing you can do, one easy trick to do, is to change your throw distance. And if you think about that giant sputter system I showed you earlier for glass coating, the throw distance between those giant cathodes and a piece of glass is about 1 inch. Now, if you're dialed into throw or deposition rate, the other thing you can do is increase the size of your cathode. So if we go from a 1 inch to a 2 inch to a 3 inch to a 4 inch cathode, we can dramatically increase the number of atoms that we're throwing at any given substrate per unit of time, and that will increase your deposition rate. It's a little expensive way to go. We can also increase the number of cathodes. And so if you really have to have a higher deposition rate, you can instead of sputtering from 1 cathode, add 2, or add 3 cathodes, and point them all at your substrate up here, and you can increase your deposition rate that way. So again, these are all tricks that you can use to increase deposition rate. Let me talk for a minute about power supplies. So everything I've talked about so far has been what we call DC, or direct current magnetron sputtering, where we're giving our target a continuous negative voltage, same number, same voltage all the time during the deposition process. If we want to sputter something which is maybe a little bit less conductive, we want to sputter something like zinc oxide, or maybe transparent conductive oxides like indium tin oxide, we can graduate to a thing called pulsed DC. And so in this case, we're going to give our target a negative pulse, and then we're going to give it a little bit of a positive pulse in order to relieve any of these positive ions that may have become embedded in our kind of weakly conductive target. And so this is also pretty handy for reactive sputtering. So in this positive pulse that we use here, that tends to maybe clean away some of the redeposition of, let's say, a nitride material that might be showing up on our titanium metal target. We can also use a thing which is called high PIMS. And high PIMS is a relatively new deposition technology, where instead of the pulses that we see here, we're going to have really massive pulses which might be a couple orders of magnitude larger than the pulses that we have in DC. And let me just mention that in pulse DC and in high PIMS, your time average duty cycle can never exceed what we were doing in direct current magnetron sputtering. So if we have a pulse like this, then we have to have sort of an off period there for the target to recover thermally before we pulse it again. And so with high PIMS now we can have massive pulses to the target, but then we're going to have relatively long off periods for the target now to thermally recover before we pulse it again. And so in traditional high PIMS now, with pulses which are on the order of maybe 2 orders of magnitude larger than the pulses here, we dramatically increase the fraction of sputter target atoms or molecules that get ionized. And if we start sending ionized sputter material at our substrate, we get lots of interesting effects of morphology. So I'm going to just talk about sputtering for just power supplies for just a second. So just to show you some cartoons. So with pulse DC, again, we've got a big negative pulse here, which sends in our argon ions, or positively charged argon ions, some of which may actually impale themselves in the body of the target. And then we do a positive pulse here, which sends in a bunch of electrons then, which mitigate any charges that may have tried to develop in our sputter target itself. And as I mentioned, in reactive sputtering, we may actually do some cleansing of any redeposited, let's say, nitride material that might start building up on the sputter track. If we want to sputter an insulator, again, everything I've talked about so far has been about sputtering things which are electrically conductive or semi-conductive. If I want to sputter an insulator, we can just kind of continue to try to increase the voltage of the target to achieve some kind of breakdown voltage. But man, that number just starts to be a crazy number, and not too many power supplies want to do that. So if we've got something which is an insulator, and I'm saying if something's got a resistivity which is more than 10 million ohm centimeters, I'm going to call it an insulator. If it's got a resistivity of less than 10 million ohm centimeters, I'm going to call it something which is resistive, and I can sputter that with my pulse DC. So if I've got a true insulator, something with a resistivity more than 10 million ohm centimeters, I've got to graduate to a thing called radio frequency sputtering. And so in radio frequency sputtering, we're sort of doing the same thing that we did with pulse DC, where we've got positive argon ions here, and then we bombard them with electrons here. But with radio frequency sputtering, we're actually varying, instead of having this nice crisp negative pulse, now we're going to vary that negative pulse a little bit in terms of its magnitude. And so it enables us to actually cleanse away any positive argon ions that get embedded in the target. But now we only have about half of the performance that we had with pulse DC. So now we're able to sputter insulators, but the deposition rate now is sort of like half of what we would have seen from a metal. And then there's a, let me just talk for one more minute about high PEMs. It's a neat technology. So again, we have these just massive negative pulses. In this case, I'm showing you something which is more than 800 volts. And by doing that, we now start to create some sputter target ions. And so remember, in our typical sputtering, we're going to send argon ions at the surface of our target. They're going to physically eject off atoms to our substrate. We're going to start accumulating a film here. But by having this massive pulse here, we're going to create lots and lots of target ions, now sputter target ions. And some of those sputter target ions will make their way to the substrate, and that additional energy will help contribute in the formation of a dense film. But some of those sputter target ions will now circle back to the target, and we'll start now sputtering the sputter target with sputter target ions, and that's called self-sputtering. And so some materials now, like copper and titanium and maybe even aluminum now, we can actually have what's called self-sputtering runaway, so that once we get this cycle going, we have enough sputter target atoms returning to the surface of the target that we're now sputtering purely with sputter target material, and we can actually reduce or maybe even eliminate that argon process gas. So if we just do a comparison quickly between the DC magnetron sputtering and high PEMs, we have the same working pressure here, but notice that the current density, the cathode current density now is 2 orders of magnitude higher than what we saw with DC magnetron. But keep in mind that the time ordered average is going to be about the same. The discharge voltages now are a little bit higher. The plasma density now is 2 orders of magnitude higher than what we see in DC magnetron sputtering. The cathode power magnitudes are just much higher. And look at this ionization fraction. In some cases, and I'll show you some images on titanium, we're going to get an ionization fraction, sort of a density of ions in the plasma itself up close to 90%. Whereas with DC magnetron sputtering, we rarely see something more than about 1%. So here's some time-lapsed imaging here, starting out at 2.5 microseconds and going up to 150 microseconds. So here's our sputter target here. Here's our magnets back behind with our magnetic field here. Notice in the very early stages of the plasma, it's dominated by argon ions. But as that plasma matures, we start to see a fairly large contribution of copper or titanium ions. And by the time we get up to 150 microseconds, more than 90% of that plasma now is dominated by titanium ions. And so at that point, you can see that the argon ions have been excluded from the plasma. And at this point, we can reduce the contribution of argon in the chamber. And by doing that, we're going to just have much more pristine films with fewer gas inclusions, much more energetic films. So our films are going to be more dense. This is just an image of copper self-sputtering. So now notice that there's none of the characteristic purple that you would see from an argon plasma. It is completely dominated by copper metal ions. If we look at metallization, again, this is a fairly old view graph there, but lots of metals do it. Unfortunately, they have to be electrically conductive. IPEN has not been demonstrated with insulators, but you can see that things like titanium, aluminum, copper, very high target ionization potentials. They're much higher than what you see with magnetron sputtering. And so if we look at thin film morphologies, things like nichrome by classic DC magnetron sputtering, you see that sort of low density columnar structures that you would see normally from that technique. By going to high PEMs, the arriving sputter target ions, much more energetic, and so we get a fully dense film, which might be even amorphous. Same thing with tungsten. Tungsten, you see these sort of classic low density triangular grain structures here in the films. By going to high PEMs, much finer grain structure, much more dense film. Again, I'm not saying that high PEMs is the answer for everything. I'm just saying it's another quiver in your or another arrow in your quiver there. That's another tool that you can use when you think about trying to deposit some of these materials. Oh, I've screwed up now. Hang on. Okay, So if we look at other film properties, things like scratch resistance, remember that things like cathodic arc have been the gold standard for scratch resistant films. And so when you think about gun barrels, hip implants, things like that, which have to be amazingly scratch resistant, cathodic arc had been the gold standard for that. But now HiPIMS has demonstrated that a much improved scratch resistance over things like cathodic arc. Because again, these arriving atoms are much more energetic. They form really nice, dense films. They're actually a lot smoother than what you would see with cathodic arc. Now, generally with sputtering, I recommend that you do pre-sputter your targets first. If you pre-sputter them with the shutters closed in your system, you can sputter away the water that's built up on the surface of the target. I mean, the target should arrive to you from the manufacturer clean, pristine, ready to go. But as soon as you take it out of the package, you're going to have water and things like that deposit on it. If your technician's pretty clumsy and he's handled it with their hands, you're going to have fingerprints on it. So again, pre-sputtering you want to do. As you pre-sputter, you want to monitor the voltage of your power supply. And when that voltage, it'll start out pretty erratic, but when it stabilizes, comes to a constant number, then you're ready to go. Again, with sputter targets, remember, you got to really keep things cool. You know, with thermal and E-beam, we were heating things. With sputtering, we've got to keep everything cool. So you've got to be mindful of the power input. Not much of the power actually goes to sputtering. A lot of it goes to heat. You need to think about the thermal conductivity of your target. Again, thicker targets are harder to cool than thinner targets. You got to think about the cooling well and whether you've got good thermal connections between the target itself. If you think about the target's thermal expansion as it gets hot, you know, it's gonna grow, and if it fits tightly into your cathode, yet that expansion may cause the thing to crack. Again, only 1% of the energy that we dump into the target itself actually goes to sputtering. Most of it goes to heat. If you look at things like copper, almost more than 90% of what you dump into that target goes to heat. So again, we can mitigate that a little bit with flow. Maybe you can have some control over your chillers so you can flow more liquid in there. But again, you've got to mitigate heat. If your target gets too hot, it's going to explode. If it's bonded to a copper backing plate, you're going to melt it off the backing plate. You might even disassociate the material. This is indium tin oxide, and you can see now this got so hot that we actually disassociated the indium tin oxide. We've got indium oxide out here, and then lots of cracking. Now, it doesn't mean your targets are always going to be beautiful. Here's a bunch of targets which have run successfully. They made great films, but over time they had lots of redeposition, lots of cracking and things like that. And so you just have to go in and clean this stuff off. So it looks horrible, but actually these targets are in pretty good shape. They just need to be cleaned. You notice that your dark space shield here has got a lot of accumulation on it here. You want to clean that off before it actually flakes off and maybe shorts out the gun. Okay, I'm running out of time, but let me talk just for a few minutes about thin film growth models. Hopefully Nate will let me run over just a little bit. So when we talk about thin film growth models, again.
Hold on one sec, JR. I just want to say I have another meeting at 1, but do feel free to stay as long as you want and take questions. And I just wanted to thank you again for coming to speak.
Okay, good.
And hopefully we can connect again in person.
Yeah.
When all this is over.
Very good. Thanks, Nate. Okay, so as I mentioned, we're really interested in the energy that these atoms have when they arrive at the substrate. That's really critical to how your films are going to form. And as these things arrive at the substrate, they're going to have an interaction. They're going to interact with the substrate, obviously, but they're also going to interact with each other. And these are kind of competing strengths. And so we'll talk more about that in a second. Again, energy is critical. We'll talk about ways to get energy into these atoms so we can form nice films. Now, as an atom arrives at the substrate, unfortunately, the first thing it's most likely to do is to bounce off. The sticking coefficients for these things are not particularly great. But if an atom lands on the substrate and it does stick, we're hoping it's got enough energy that it can move around and find a friend, find another atom, and start to form either a monolayer or a cluster. Now, typically speaking, most of these arriving atoms are more attracted to each other than they are to the substrate. And so they're going to tend to form clusters. And over time, these clusters will grow in size and hopefully integrate with each other. So again, we talked about the mobility of these add atoms. It's really, really critical when these films form. And we can affect that with things like heat. So maybe we want to heat our substrate up so that we can add some energy as it hits the substrate. We may want to use an ion assist. So we may want to add an ion gun to your system and send some more ions from that gun directly at the substrate to try to bombard these things. In a perfect world, we would love to engineer some kind of a chemical reaction of these add atoms with the substrate. And if you look at processes like atomic layer deposition, that's specifically designed where you actually physically engineer a chemical reaction between these add atoms and the substrate. And in those cases, you get the best adhesion, the best bonds. It's really, really wonderful if you can do it. And then there's some other things that we can do. If we want to affect things like grain orientation of our films, we can use things like epitaxy. And I'll show you an example there. So if you would do an internet search on thin film growth models, you'll always see these three, the Frank Vandermeer model, the Island growth model, the Vollmer-Weber, and then the Stransky model. So the Vandermeer model is a little bit naive in that it says that we're going to form a monolayer, and then the next add atoms then will form another monolayer, and that each subsequent arriving add atom finds a vacancy there and fills in that monolayer. This almost never happens, even in atomic layer deposition. Typically, what you're always going to see is what's called island growth, where these add atoms are more attracted to each other than they are to the substrate. And so they tend to form clusters, and will form lots and lots of clusters over time, and eventually those clusters will grow into each other and we'll get a continuous film. Now, you do have some rare occasions where we actually have in the Stransky model, where we've got the first monolayer, the first couple monolayers where the add atoms are very attracted to the substrate, but as we get away from the substrate, that attraction drops off and then we start forming clusters. So again, I don't want to spend too much time with this, but again, mostly what you're going to do when you're doing these films are going to be Vollmer-Weber models. And if you look at the sort of progression of thin films over time, starting out at ½ a minute and going up to an hour and a half, you see some small clusters form. Subsequent arriving add atoms tend to join to these existing clusters and make them larger and larger and larger until eventually they acquiesce into each other. If you look at just two different clusters over time, you can see that one cluster, as subsequent add atoms arrive, they tend to join those clusters together, and then eventually you get larger and larger clusters. The Stransky method is also very, very interesting. It just means that you've got lots of attraction at the initial one or two monolayers, and eventually that attraction drops off and you form clusters. As I mentioned, we can also affect this with heat. So if we are depositing onto a relatively cool substrate, we get lots and lots of small clusters. As we increase the heat on those clusters or on that substrate, we can reduce the number of clusters or make them larger clusters. We can also do some post-deposition substrate heating sometimes to actually take a porous film and actually make it more dense. We can also use epitaxy, so we can match the characteristics of the substrate with the film that we're depositing. We did this a lot in high temperature superconductivity. Most of you are not old enough to remember what that is, but a lot of great work went on at Northwestern in high temperature superconductivity. And in that case, we would use things like single crystal magnesium oxide substrates, which were lattice matched to the yttrium, barium, copper oxide films that we were depositing. And with that lattice matching, we grew these beautiful C-axis oriented films. And in a polycrystalline film that's not oriented, we would get critical current densities of maybe 100 amps per square centimeter of cross section. If we could grow beautiful C-axis oriented films, we had current densities here which were 10 million amps per square centimeter of cross section. So grain orientation matters. Now, back in the 60s, there was a real cry from the semiconductor industry for people to come up with predictive models of process parameters that you can control that would then affect the morphology of the films that we grew. And so you could use things like substrate temperature, pressure in the system, bias voltages, the ratio of the substrate temperature to the melting temperature of the material you were depositing, deposition rate, angle of incidence. There's all kinds of things that we could affect. And by playing around with those, we could change the morphology of the films we develop. So this is a very, very simple model. This particular one only uses chamber pressure and the ratio of the substrate temperature to the melting temperature of the material, but these models are much more complex than that. But I'm just showing you two parameters here, and this is what? Chrome nitride. So I'm just showing you with chrome nitride, just by varying temperature and chamber pressures, we can make all of these different morphologies. And just notice that there's zones here, zone 1, zone 2, zone 3, zone T, and those zones have all got particular grain structures. And just notice that we can get these different grain structures by varying the substrate temperature relative to the melting temperature of the material. And all of this has been worked out for you. So if you want a particular morphology, if you want something with the morphology of zone T, we've got some coaching for you on what that substrate temperature wants to be. Again, it's been worked out for all of these various zones here. And obviously the temperatures for silver are going to be different than the temperatures for nickel or for titanium. But we don't have time to talk about each individual zone, but just know that there's a lot of work already published there to help you affect the morphology of your films. And things like stresses. You may want your film to be in compressive stress, and if you're trying to measure it, that means the film is going to be bowed up towards you. You may want the film to be in compressive stress. That may affect the properties that you want. In that case, the film's going to be bowed away from you. It might have a surface of the film which looks like the desert after a rainstorm, big cracked areas there. Your processes may have sort of integral stresses, where you may have thermal stresses, which are caused by the mismatch of the coefficient of thermal expansion and the substrate itself. You may have some process-based stresses, where low pressure processes are different than high pressure processes in terms of the stresses that they impart to their films. If we go back to that structure zone model where we've got chamber pressure here and substrate temperature here, just notice that I can generate a variety of stresses in my films by varying these parameters. Again, if we look at just pressure, for example, films that are done at relatively high pressures tend to be in compressive stress. Films, think about sputtering. Whereas films done at low pressures tend to be in tensile stress. So think about thermal evaporation. Now, here's 6 films. If I was in front of you giving this lecture, I would make this a quiz, and I would say, look at these 6 films and tell me which one is the good film. And this is a cruel question. The answer is, it depends. It depends on what you're trying to make. If you were trying to make great optical films, maybe you want dense films with few grain boundaries. If you're trying to make catalysts, maybe you want films with the surface area of cauliflower. But we can do all of these things. We can generate all of these different morphologies by playing around with the deposition parameters that I've talked to you about. Again, these are wonderful processes. I'm just thrilled to be able to be with you and actually go through some of this stuff. Again, there's my contact information. Again, I would welcome emails from you. You can certainly hook up with me on LinkedIn, and we can dialogue that way. Again, happy to have had the opportunity to do this with you, and hopefully in the next 6 months or a year or so I can do it again in person. This lecture typically takes 4 hours, and so I've tried to crush it down into a little bit more than 2 for you. So any questions? If there's questions, I'd be happy to answer them for the folks that survived this long. Yeah, I don't see any questions. Okay, if you do have questions, just send them to me by email. Otherwise, thanks again for attending, and take the rest of the day off.
Thank you, JR. We appreciate you being here for us.
Yeah, take care.
Thanks, JR.
Yep, thanks, bye.